Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about a topic from linear algebra, orthonormal coordinate systems. The problem that we will solve is expressing a vector y as a linear combination of a set of other vectors called a basis. That is, we will find the constants by which you have to multiply each vector in your basis so you can get the vector y. Okay, y is going to be a generic vector. Okay, we will see that finding these constants is very easy if we have a nice basis, an orthonormal basis. We care about this, about these constants, about these weights, because in the near future we will study them from a statistical perspective. To be more specific, we will find confidence intervals and carry out hypothesis tests for these weights. As usual, let's discuss an example to make our illustration more concrete. Okay, so I'm going to present you a set of 3 vectors that live in R3. Okay? I claim that these 3 vectors are orthogonal. And let me remind you that by orthogonal, what we mean is that the inner product between them equals 0. And in this case, the inner product that we're going to be using is the Euclidean inner product between vectors. Okay? So the first vector that we're going to have here is 1, 1, 1. Remember that we think of vectors as column vectors. So the next one is -2, 1, 1, and the third one is 0, -1, and 1. I claim that these guys are orthogonal, and I want to again remind you that we're going to be interested in the idea of orthogonality and eventually in orthonormality, because we want to be able to express y, the a generic vector, as a linear combination of a set of vectors that form our bases. In this case, v1, v2, and v3 would be the bases, and these weights, these constants that multiply each member of your bases, are the coordinates of y with respect to that basis. Okay, and it turns out we're going to see in just a few minutes that it's a good idea to be dealing with orthonormal bases, because then finding these weights is going to be easy. Okay, but first let me show that v1, v2, and v3 are orthogonal. Okay, so let's show that v1 is orthogonal to V2. Okay, and then if we get the idea for that one, then we can recycle that idea for the others. Okay, and remember that the Euclidean inner product is the one that we are going to be using. So in this case, it would be the Euclidean inner product between V1 and V2 would be 1 times negative 2 plus 1 times 1 plus 1 times 1. Okay? Okay, so to do things quicker, let's use R. Let me launch R here. So V1 is going to be matrix with only one column, which is, you know, a vector. So 1, 1, 1. Again, as usual, we're using that C function, concatenate. We want only one column. That should do it. V1, yeah, that's the one we want. Let's do something similar with V2. That guy is going to be negative 2, 1, 1, 1. Perfect. Okay, so what we wanted to show is that the inner product between the Euclidean inner product between V1 and V2 is 0. So what we want is transpose of V1 and then matrix multiplication with V2. Okay, so 0. And as we said, the definition of the Euclidean inner product between these two guys would be V1 times negative 2 plus 1 times 1 plus 1 times 1, and yeah, it gives 0. Now let me define V3. We might as well, might need it. And that guy here, let's look for it, is 0, negative 1, and 1. 0, negative 1, and 1. V3, there we are. Okay. So in a similar way, we can show that V1 is orthogonal to V3. So it would be transpose of V1 times V3, 0 again. And we can also show that V2 is orthogonal to V3, 0. Okay? So we have a set of, again, the inner product between any pair of those three guys, of those three vectors, is going to be 0. So they form a set of three orthogonal vectors, so they form an orthogonal basis in R3. Okay? So let's write that down. So we have a set of three orthogonal vectors, and they form bases in R3 in the space, right? Okay. And what that means, okay, is that if y is a generic vector in R3, okay, then you can express y as a linear combination of v1, v2, and v3, okay, where these guys, w1, w2, and w3 are coefficients, are constants. Okay? Okay. Now, if you want to find that decomposition of y in terms of the members of your bases, it turns out that if the norms or sizes of the vectors v1, v2, and v3 were 1, we could easily find those weights. Okay? So we will find vectors u1, u2, u3, which represent normalized versions of v1, v2, and v3. Okay? And what we're going to show is that w1 is just the inner product between y and u1. w2, inner product between y and w2, and w3, the inner product between y and w3. So let me just write that down. It turns out that if the norms, again, or sizes of vectors v1, v2, and v3 of the vectors, let me say it like this, of vectors in your bases, were 1, we could easily find w1, w2, and w3. Let me say this, we will show that wi, as in a generic weight, is going to be the inner product between y and ui. Okay, again, we're going to be using this as a notation for the Euclidean inner product between y and ui in this case, right? Let me just say that ui is a normalized version of vi, where ui is a normalized version of vi, meaning vi but divided by its norm. And we're going to be using that notation for the norm or the size of your vector. Okay? Okay. So first, let's recall what the squared norm of v1 is. Okay? Recall that the squared norm of v1 is just since v1 is 1, 1, and 1, what we have here would be 1 squared, oops, plus 1 squared plus 1 squared, which is just 3. Okay, and then that means that the norm would be square root of 3, right? Make sense? Okay. So let's check with R. It would be just like this. Transpose of V1, matrix multiplication with V1, right? That would be the square norm, but what we want is square root of that guy. Okay, so it would be square root of that guy, square root of 3, which is that. Okay. Okay. So what we're going to be doing is we're going to be defining u1, in this case u1 would be just v over the square root of 3, right? So let me write it down like that. So that's what we meant by this, that ui, like in this case, u1 is going to be v divided by the norm of v1. Okay, u1 equals v1 divided by its norm. Okay, make sense? Okay, so let's check that the first norm is 1. Let's define each of those guys just using this recipe. So we already have v1, v2, and v3. So let's define u1 as v1 divided by the square root of, and let me be careful here, we know that this is the norm, right? Well, yeah, we know that this is the square norm, 3 in this case, right? And then I want the square root. But see that we have a 1, 1 here, we have something that looks like a matrix. So I just want to make sure that R is regarding this as a number. So as numeric, that's a squared norm of v1, then we take the square root, and what we're doing is v1 divided by the square root of the square norm, meaning just the norm. That's going to give you your guy here. Okay, so that would be u1, this guy here, 1 over the square root of 3 in this case. We could do the same with the second one, just v2 divided by its norm, right? And u3, same thing, v3 divided by its norm. And then we can check if I did this correctly, right? We can check that the norm is 1. Okay, so if the norm is 1, well, the square norm is going to be 1 as well, right? So 1. We can check that the square norm of u2 is 1, and finally that the square norm of u3 is 1. So now u1, u2, and u3 are not only orthogonal. Now these guys are said to be orthonormal because they are orthogonal and their norms are 1. Okay? And again, let me remind you that we wanted to do this because it's going to be easy for us to find those weights. Okay? So in our lecture notes, I prepared an example where we see that y, a generic vector in R3, can be easily expressed as a linear combination of u1, u2, and u3. Okay? Makes sense? So next, that's what we're going to be doing next. Next, we will show that y can be expressed as w1 times u1, w2 times u2, and w3 times u3. It's going to be a u1. This one is going to be a u2. This one is going to be a u3. Okay? Okay. So let's go to our lecture notes. Yeah, that's the example that we want. See, here we already have the normalized versions of v1, v2, and v3. Okay, so what we're going to be doing is expressing y as a linear combination of these three vectors, u1, u2, and u3. And what we claim is that it's going to be really easy. Okay, so let me walk you through it. What we're saying is, hey, if you want w1, the weight, the coefficient for the weight that is going to be multiplying the first member of your bases, u1, it's going to be easy because u1, u2, and u3 are orthonormal, meaning they are orthogonal and their norms are 1. Okay? What we claim here is just take the inner product between y and u1, and that's going to give you w1. So if you do that, it would be just 1 over the square root of 3 times y1, 1 over the square root of 3 y2, 1 over the square root of 3 y3, and you add them all up. That's the inner product, right? Because the generic matrix, the generic vector y is going to be first coordinate y1, second coordinate y2, third coordinate y3, and that multiplied by 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. Make sense? Okay, so now note that we could express, note that the product between, this is just the w1, this is just the weight that we have in this expression, okay, w1. But if you do the product w1 times u1, note something interesting. That w1 times u1 would be this times 1 over the square root of 3, this guy. So it's just going to be square root of 3 times square root of 3. Hey, that's just a 3, right? And that's what you have here, right? That would be the first entry. Same thing goes for the second one. Same thing goes for the third one, right? Because u1 is 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3 times this. You end up with the same. But this, if you take a look at this, y1 plus y2 plus y3 over 3, that's the same as y bar in this case. Okay? So, if you wanted to find w2, it's going to be equally simple, right? Just find the inner product between your generic coordinates y1, y2, and y3, and then you know, with w2, in this case w2 happens to be this guy here. Okay, so when you do the algebra, you end up with this. Okay, and that's just the coefficient, the multiplier that is going to affect u2. And then when you do this, w2 times u2, you end up with this. Okay, last weight, w3. Just find the inner product between y and u3. u3 happens to be this guy. So if you do the math, you end up with this. And if you find the product between w3 and u3, you end up with this. Now remember that what we said is that we would like to show that a generic vector y1, a generic vector y, and again let me just remind you that what we are thinking of here is that y has generic coordinates y1, y2, y3. So a generic vector y that lives in y3, in R3, sorry, the space looks like this, right? It's generic. y1, y2, and y3 could be any number. So what we're claiming is that now we have an easy way of expressing y as a linear combination of u1, u2, and u3, that we can find these guys easily. Okay? Okay, so we have a way of finding w1, w2, and w3 easily using inner products, right? It works that easily because we have an orthonormal basis. u1, u2, and u3 are orthogonal, and their norms are 1. Okay, and now let me just show you that the first coordinate is what we want. Okay, so you have y1 plus y2 plus y3 over 3. That's the same as 2 times y1 plus 2 times y2 plus 2 times y3 divided by 6 is the same, right? So if we do the sum of this plus this plus this, I claim that we should end up with y1. Okay, so here we go. Note that you have 2y1 plus 2y2 plus 2y3, okay, divided by 6. Note that you have 4 times y1, so that would be 6 times y1. And then you have negative y2 plus positive 2 times y2, right? Negative 2 times y2 plus 2 times y2, those guys cancel out. Negative 2y3 plus positive 2y3, those cancel out, so you end up with 2y1 plus 4y1, 6y1 divided by 6, that's y1. Okay, And then if you do the same with the other coordinates, with the second and the third, right? If you add them up, you'll see that you will end up with this, what we wanted, that the sum equals y1, y2, y3. Make sense? Okay. So, let's recap. We just did the following. Okay, let's recap. We just did the following. We turned a set of three orthogonal vectors v1, v2, v3 into an orthonormal basis u1, u2, and u3. Okay? The difference between orthogonal and orthonormal bases is just that a set of orthonormal vectors are a set of vectors that are orthogonal, but in addition they have a norm of 1, all of them. Okay? And why did we do this? We did this because we wanted to express any vector y, in this case in R3, as a linear combination that looks like this, right? And why did we want to do that with an orthonormal basis? Because then finding W1, W2, and W3 is easy, right? Then the weights, the Wi's, are just going to be the inner product between y and the corresponding u. Okay? So in our particular example, our decomposition will look like this, right? Y equals W1 times U1 plus W2 times U2 plus W3 times U3. But note that what you have is this. Hey, this vector is, oh, y bar times this vector plus whatever is left. Well, we're going to talk a little bit more about these decompositions, again from a statistical perspective, and how we are going to be doing hypothesis tests and finding confidence intervals for some of these weights, for some of these W's. Okay? Well, that's it for now. Take care and keep working hard. See you next time. Bye.